Hey guys, I have your notes here for day 2 of limits. So in day 1 of limits, remember I kind of taught you the general concept of a limit, and we did a visual approach. So we looked at a graph of a function and found the limit as x approaches some number. And limits are really cool and they're pretty easy when you have a graph. What if you don't have a graph and you're not allowed to use your graphing calculator? You just have an equation of a function. And you're asked the question, as x approaches some number, as x gets closer and closer and closer to some number, without a picture, tell me where your y's are headed. As x gets closer and closer to a number, where is your function? How high is it? How low is it? Where are the y values headed when x is headed toward this number? Without a picture, we're going to be able to determine that. So we have kind of some steps to go through to figure out the answer to some limits without a graph. So plan A, we're going to use direct substitution. So as x approaches some number, we're going to take that number, we're going to sub it into our function, we're going to cross our fingers and hope we don't blow up. If we don't blow up, we have our answer. Oftentimes, we're blowing up. So we need a plan B. So if plan A causes us to blow up, let's not do that. Let's do plan B. Plan B says try to manipulate your function. Try to use algebra to do whatever you can to see where your y's are headed. We might factor, we might cancel, and then once we can simplify it a little bit, then we're going to try direct substitution. Again, cross our fingers, hope we don't blow up. If that doesn't work, the last thing we're going to try is we're going to try plugging in x values super close to whatever number we're trying to do a limit near. But I want you to plug in numbers on both sides. Plug in values on both sides of A. So, for example, if you're doing a limit as x approaches 2, plan A, you blow up. Plan B doesn't work. If you move on to plan C, think of some numbers super close to 2 from the left of 2, so just underneath it, just smaller than 2, and to the right of 2, just a bit bigger than 2. Because remember, when you do the limits graphically, you have to say, okay, where are my y's headed from the left? Where are my y's headed from the right? Do they match? So we have to look at values to the left of 2, so just barely beneath 2, and to the right of 2, just above 2. Or, what if you're doing a limit as x approaches 0? A number just below 0 is going to be negative 0.0001. And I kind of picked these at random. I mean, you could have picked 0.00000001. Whatever. I picked a pretty small number close to 0. And then to the right would be the positive version of that. Super close to 0, right? Okay, so plan A, plan B, plan C, we're going to try them all if necessary. Here we go. First one, let's look at this example. The limit as x approaches negative 2. I would like to know, for this function, where are my y's headed when x gets close to negative 2? So I'm going to use direct substitution. I'm going to directly sub in negative 2 everywhere I see an x. I'm going to do the math either in my head or on my calculator, and I get 13. There you go. I didn't blow up. There was nothing funny about this. Nothing ever caused me to blow up by subbing in negative 2. So as x gets close to negative 2, my y's are headed toward positive 13. And if you think about it, you know kind of what this graph looks like, right? It's just a normal parabola. There's nothing weird going on in this function. Parabolas don't have holes. Parabolas don't have asymptotes. Parabolas don't blow up. So direct substitution works here. Let's check out example 2. Not such a common function. You probably don't know what the graph of that looks like already. It's okay. Let's try to find the limit as x approaches negative 2. Sub it in and find out. So sub in negative 2, sub in negative 2. Turns out I get positive 5/2. So as x gets close to negative 2, my y's are headed toward 5/2. Does this function ever blow up? It does. It does blow up when x is positive 2, but you know what? That had nothing to do with the problem I was doing. I wasn't looking at positive 2. I was only looking at x values close to negative 2. So for what I was doing, we never blew up. Alrighty, next one, direct substitution. Now often when I do direct substitution, if there's a denominator, I sub it in the denominator first, because if you're going to blow up, it's going to be because of your denominator. So why even do the math up here yet if there's a chance that you're going to blow up down here? So I sub it in the denominator first. Sure enough, when I sub in negative 2, I get, I don't care, over 0 because I just blew up. So direct substitution failed. Let's move on to plan B. Plan B says factor and try to cancel. Okay? So I factored my numerator. I unfoiled it. I factored my denominator. Now check this out. Ooh, first semester pre-cal. Do you know what is going on when x is negative 2? When x is negative 2, this quantity is 0, this quantity is 0. So when x is negative 2, it's in both places, right? That means the function, the function has a hole at negative 2. That's why it's blowing up. When I try to sub in negative 2, there's a hole there. That's why it's blowing up. So here's what I'm going to want you to do. I'm going to say we're going to ignore the hole. Because remember, when we're doing a limit, I really don't care what's happening at negative 2. Who cares that there's a hole there? I want to know, where are the y's as we get closer and closer and closer to this hole in the function? Where are the y's headed? So we're going to ignore the hole. So I'm going to cross them out, and I'm going to say ignore the hole. You know what you're going to say? I'm going to cancel them. Okay, you can cancel them. But technically, when you cancel them, you just divided by 0 and you blow yourself up. But that's okay. If you want to blow yourself up, that's your prerogative. I'm going to say ignore the hole. So we're ignoring these two quantities. If I ignore these two quantities, look what I have. I now have this one and this one. Because without the hole, this is what's left. Okay, so this is what's left if I ignore the fact that there's a hole there. Now, sub in the negative 2. Sub in the negative 2 and I get this, which reduces to 3/2. Yes, there is a hole at negative 2, but on each side of the hole, guess where my y values are headed? My y values are headed toward 1.5. And I can only figure that out if I ignore the hole, because this right here is causing me to blow up. If I ignore that, then I don't blow up anymore. Okay, next one. As x approaches positive 2, direct substitution. Again, I see that I have a denominator. The numerator is going to be fine. I'm going to sub it in my denominator first. Sure enough, I blow up. Plan B. Let's factor this. Plan B. Factor that. It's not factorable. Okay, on to Plan C. Plan C says, look at what we're getting close to. Think of numbers super close to 2. a little smaller than 2, a little bigger than 2. We have to look on both sides. So here's what I do. 2x plus 5, x minus 2. I take the function 2x plus 5, x minus 2. I sub in a number just below 2. Super close to it, but just below it. So I subbed in 1.99999. I used 5 nines. I got pretty close. Make sure you sub in the same exact value down here, okay? Because if you use 5 nines up here and only 4 nines down there, something weird's going to happen. You don't want to do that. So make sure you sub in the same number, okay? You can type it in your calculator. And when I typed it in my calculator, I got negative 899,998. That is a super huge negative number. Now, to the right of 2, I want you to sub in another number super close to 2, but this time on the right side of it. So I chose 2.00001. Sub it in both places. Do the math. I got 9,900,002. Okay, so on the left side, as x approaches, as x is getting close to 2 on the left, where are my y's headed? Way down to negative values. However, jump to the right side of 2. As I'm super close to 2, where are my y's headed? Oh, super huge positive values. So I think what we've got going on here is headed down that way, headed up that way, surrounding x equals 2. Do they match? No. Does the limit exist? No, because the left side didn't match the right side. The limit does not exist because I checked the left and I checked the right and they didn't match. In fact, when you have a function, let's see, at x equals 2, if you have a function that's headed down super far on one side and up super far on the other side, it means you have an asymptote at x equals 2. Does that make sense? That you would have an asymptote at x equals 2? Well, if you remember anything from first semester pre-cal, doesn't 2 make your denominator 0, but not your numerator? If there's a number that makes your denominator 0, but not your numerator, that's an asymptote. Vertical asymptote. Okay. That was just kind of bonus information. That was just for fun. So you saw me do plan C. Plan C, checked a number from the left, checked a number from the right. The left side and right side limits did not match, therefore the limit does not exist. Okay, here's another one. Direct substitution, boom. Factor, nope. Plan C. All right, so I'm going to choose numbers super close to 0 from the left and super close to 0 from the right. So I chose from the left negative 0.00001 squared. Now, here's what I want you to do. We're going to try this without our calculator. Okay? Try this without your calculator. Ready? Take a negative tiny number, and square it. What do you get? When you square this, what do you get? You don't have to carry and move your decimal. Just think about it. Describe it to me. Square a negative tiny number. What do you get? You get a positive. Teeny tiny number, right? Because where am I? 0.00001 times 0.00001 is 1. And how many places would you have to move your decimal over? 10. .00001. That is a teeny tiny number. Positive, teeny, tiny. No calculator. Brain. Ready? Some positive, teeny tiny number. Now, when you take your numerator divided by this positive, teeny tiny number, what do you get? Now, some of you might need your calculator to kind of grasp this concept. So maybe try it. Do 4 divided by point equals. What do you get? You get a positive, huge number. From the left of 0, this function has huge positive y values. Let's try the right side. So let's do from the right. So I subbed in a number super close to 0 on the positive side, right? So it kind of mirrors that one. Ready? Positive 0.00001. Square it. What do you get? You get positive, teeny tiny. And 4 divided by positive, teeny tiny is positive, huge. Do they match? They do. So what's the answer to your limit? Well, on the left, it's heading up to infinity. On the right, it's heading up to infinity. Where is it? There we go. So the answer to my limit, where are the y's headed? The y's are headed to positive infinity. Okay, moving on. We're going to try this one without a calculator as well. Brain power. Here we go. This is kind of what I call concept math. Not punch buttons math, concept math. Here we go. Direct substitution. Sub in -3. You blow up. Trust me. I already did it. All right, plan B. Let's try to factor and let's try to cancel. So I factored it. Woohoo! I said it, didn't I? Let's see. This one and one of these, we are going to ignore the whole. Ignore the whole. If you ignore the fact that there's a hole there, it's what's causing me to blow up. Ignore the hole. Here's what's left. Here's what's left when you ignore the hole. So I'm going to do a rewrite. When I ignore this hole, I have this left, and I'm still trying to do a limit. Okay? Now, when I try direct substitution, by the way, the moment you try direct substitution, you drop the fact that you drop the word limit, right? So this is a limit. Here I'm trying to get the answer to the limit, so I don't need to write limit anymore. So I do direct substitution. Well, doggone it, I still blow up. Dang, I thought plan B was going to work. Turns out I'm still blowing up. Now let's move on to plan C. So I know there's a hole there, so I'm still ignoring the hole. So I'm still focusing on this. Plan C, ready? I'm gonna sub in a number to the left of -3. So on a number line, think about a number to the left of -3. That means I'm just a little bit toward -4, right? So I'm going to choose -3.00001. No calculator. Let's see if you can do this in your head. So negative whatever -1. This negative combined with this negative is just going to get me a larger negative. So I'm going to call the numerator -4-ish. You know, because I might have used 5 decimal places and you might have used 4 decimal places, whatever. When we sub in a number to the left of negative 3, we're going to each get about negative 4 over. Okay, ready? Negative, so a bigger negative than 3 is this. Add 3 to it. What do you get? Okay, well, think about this. Do I have more negatives here or do I have more positives here? I have more negatives. How many more? Not many. Not many at all. Just a very tiny amount of negatives when I combine those two values. So I'm going to call this negative tiny. Right? No calculator. So a negative divided by negative gets me a positive. And 4-ish over a tiny number. 4-ish divided by a tiny number is going to get me a huge result. So I think from the left, my y values are headed toward positive infinity. Let's try from the right. Again, sub in a number, no calculator, just think about it. A number just bigger than 3, and I'm going to subtract 1, I'm going to get a number just bigger than 2, right? So I'm going to call this hang on, that's silly. I subbed in the wrong thing. That's silly. What was I thinking? Negative 3, negative 3. So to the left of negative, to the right of negative 3, crazy, crazy, crazy. Okay, that'll work. Yeah, on a number line, negative 3 means you back up toward 2 just a bit. There we go. So this minus 1 is going to get me negative 3-ish. Negative 3-ish. Just kidding. That's negative 3-ish. Minus 1 is going to get me negative 4-ish. I'm telling you to use your brain, and yet mine's not working. And then combine these two. This is almost negative 3, but not quite. So let's see. Do I have more negatives or more positives here? I have more positives. How many more? Not much. Just a teeny tiny amount, or a tiny amount. I have a tiny amount of positives left. Positive, tiny. Okay? A negative divided by a positive is a negative. And 4-ish divided by a tiny number. How many times does a tiny number go into 4? A huge amount of times. Okay? So from the left side, I get positive huge values. From the right side, I get negative huge values. Overall, I can say that the limit does not exist. Does not exist. Okay. Now we're going to do limits at infinity. So we're not just looking at around a particular number. Limits at infinity, it's saying look way right on your graph or look way left on your graph. Where is your function? So if I turn my head toward the positive infinity direction, where are my y's? Are my y's way up there? Or are they way down there? Where are they headed? That's what we're trying to figure out. Okay, so the limit as x approaches infinity of some crazy function. Oh my gosh, this looks awful, doesn't it? So you're welcome. I did the math for you. I subbed in large values of x because we're looking as x goes to positive infinity. So if x is 100, or bigger, 1,000, or bigger, 10,000, or even bigger, 100,000. So I subbed them in and I did the math, and here's what I got from my y's. Negative 0.995. Negative 0.995. Subbed in that number, this is what I got from my y. Subbed in that number, this is what I got from my y. Okay? You see a pattern. As x gets huge, as x goes to infinity, where do you think these numbers are headed? Negative. What does it keep getting closer to? 1. I think that this is headed toward -1. Can you kind of say that with confidence? Like, yeah, I think that's headed toward -1. If you can't say it with confidence, plug in a bigger number, and then a bigger number, and then a bigger number. At some point, you'll be kind of confident. Next one. How about as x approaches -infinity? Okay, I have a calculator. I'll sub in -100, -1,000, -10,000, -100,000. Here's what I get from my y's. And then -1,000, I get this. And then a bigger negative, I get this. And then a bigger negative, I get this. I mean, do you really think it's headed toward 0.571? Do you think maybe it's headed toward 0.5710? Or maybe it's headed toward 0.5700? Maybe it's headed toward 0.57140 or 11290, you know? I think that's kind of hard to say. I don't know. I can't answer that with very much confidence. Okay, here's the cool thing about this function. This function is a cubic, a polynomial, over another cubic, a polynomial. I'm going to show you some cool tricks to do with limits and polynomials. There's this thing called the limit theorem. Okay, it's going to look awful. It is going to look awful, but it's not that bad. Suppose you're doing a limit of a polynomial over a polynomial. Here's what I want you to do. Think of each term as its own little function. No big deal. So, it's the limit of, think of this by itself, minus this by itself, plus this by itself. Just think of it in pieces, okay? We got this piece and this piece and this piece, and then we got this piece and this piece. What we can do is we can do separate limits. So if we've got pieces and pieces, I can do the limit of each piece. So I can do the limit of this piece and 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 the limit of this piece. Why on earth would I want to do that? I'll show you. But first, a couple of basic limit laws. You ready? The limit, as x approaches anything, the limit of a constant equals a constant. Here's what I mean by that. Suppose you have a function, y equals, and it's just some number like, I don't know, 3. Y equals 3. It's some constant. Wouldn't your graph look like this? Y equals 3? Ready? As x gets close to 0, where are my y's headed? Well, aren't they always 3? Okay, trick question. As x gets close to 10, where are my y's headed? As x gets close to 10, my y's are still 3. If your function is a constant, it doesn't matter where your x is headed. Your y's are always going to be that constant, okay? So this limit law, we call it the limit of a constant. The limit of a constant is just the constant. The limit, if this is just some number, your answer to the limit is just that number. Super easy. Next one. What if you have something like this, 1 over x to the n, as x goes to either positive or negative infinity? Well, here's the answer. Let me show you why. Sub in infinity for x, right? As x gets close to, sub in infinity. Now, if you ever tell anyone that I wrote this on my paper, I will deny it to the death. You can't sub in infinity. Infinity is not a value. But I just want you to think about it, okay? Take some ginormous number and raise it to any power. Wouldn't this denominator be even more ginormous? Okay? What is 1 divided by some huge number? How many times does this huge number go into? Well, it doesn't. So, if you don't believe me, try 1 divided by 5 million on your calculator. You're going to get some super tiny number, right? So 1 divided by some huge number results in a tiny answer. How tiny? Well, close to 0. It's so tiny. So I'm not saying the tiny is 0, I'm saying the limit, right? As this gets bigger, this answer gets smaller, so that where are my y's headed? Because they're getting so small, my y's are getting smaller and smaller and smaller and smaller, and they're headed toward 0. So I'm saying, as x gets huge, my y's get close to 0. Super important. Okay, ready? Let's go back to this polynomial over a polynomial thing. This is going to look awful, but I'll try to get through it as quickly as I can. I've got a polynomial over a polynomial, and we want to know, as x approaches infinity, where is this headed? Ready? Find your greatest exponent, and I want you to multiply your numerator and your denominator by 1 over x to your highest exponent. So my highest exponent in the whole thing is x cubed. I'm going to multiply by 1 over x cubed and 1 over x cubed. Ready? Here I go. I'm going to distribute it on the top, and I'm going to distribute it on the bottom, and I'm still doing a limit. Whew. Looks kind of yucky. Okay? Now, reduce. Reduce, reduce. That can't reduce. That's what I get. Yes? Okay. Remember that thing where I said if you've got like pieces on the top and pieces on the bottom, you can do the limit of each piece? Oh my gosh, this looks awful. Okay, here's what I did. I wrote out the limit for each piece. Wrote out the limit for each piece. Ready? As x approaches 4, what's the limit of a constant? It's the constant. So the answer to this piece right here is 4. Let's do the next piece. Ready? As x approaches positive infinity. Okay, so as this gets huge, what's 4 divided by huge? Tiny. How tiny? Well, close to 0. So the answer to this piece is like tiny. Was it minus or plus? It was a minus. 4 minus tiny. Okay, so like 0-ish. Plus. Next piece, ready? The limit here. So ready? Plug in infinity. Cube it. Hold on. This denominator is ginormous. 5 divided by ginormous is teeny tiny. Or how about 0-ish? Okay? Next one. This piece, as x gets super big, 6 divided by huge, tiny. Or like 0-ish. Minus. The next one is another tiny. And the next one is another tiny. right? Now, what is all this? Well, the numerator. 4 minus whatever, it's so small it's irrelevant, plus whatever, it's so small it's irrelevant. So let's call it 4. 4 over 0? No, not exactly. 4 over something tiny. The limit is 0. They're headed towards 0, but they're not there yet. So this becomes 4 over tiny, and 4 over tiny is huge. So this limit, ready? For this function, as you look way out to infinity, where are the y values headed? Way up to infinity. Quickly take you through another one. Quickly, and I mean quickly. Polynomial over polynomial. Look for your biggest exponent. It's x to the 5th. Multiply everything by 1 over x to the 5th. I went ahead and did it and simplified. See my pieces? Here are my pieces. In my head, I'm going to do the limit of each piece. As x approaches infinity, this is headed towards 0. This is headed towards 0. This is headed towards 0. So it's kind of like 0-ish on top. 0-ish. Or something tiny. Bottom, 6. Sorry, I should have said the limit of a constant. The limit is as x approaches infinity. 7 over huge, 0-ish. 2 over huge, 0-ish. 4 over huge, 1 over huge. Now, the answer is not. This is some number, some very, very, very small number, and it just keeps getting smaller and smaller and smaller, divided by 6-ish. So a teeny tiny number divided by 6 is going to result in a teeny tiny number. So I'm going to say the answer to my limit is 0. Remember, it's asking where are the y's headed? Well, the y's are getting tiny. So they're headed towards 0. Okay, last one. Polynomial, polynomial. Highest exponent, c. Multiply by it, c. Let's do the limit of each piece. The limit of a constant is 4. Limit, 0-ish. Limit, 0-ish. What's my numerator? 4-ish. Denominator, limit of a constant, 7. Limit of this, 0-ish. Limit of this, 0-ish. Limit, 0-ish. So all of these are kind of irrelevant. This is kind of like 4-ish over 7-ish. Where are my y's headed? My y's are headed to 4/7. My y's are headed to 4/7. One more thing before you shut me off. By the way, 4 divided by 7 is like 0.571428,571 and so on. Did you notice that when I started rushing through this problem was the same as this one? We couldn't tell exactly where the y's were headed by just plugging in super large numbers. But by looking at a polynomial over polynomial, multiplying by here's what I got, 4/7.